An introduction to this webinar. It's how AI is shaping the future of PCB design. And I want to introduce our speaker today, which is Sergiy Nesterenko. He is the founder and CEO of Quilter, which is a software company that uses AI and machine learning to automate PCB design. Prior to founding Quilter, he was a senior radiation effects engineer at SpaceX, where he was responsible for the performance of Falcon 9 and Falcon Heavy electronics in high radiation environments. Sergiy has a background in physics, chemistry, and math, and has been featured on popular AI and electronics podcasts like Amp Hour, The Bomb, and Robert Farrank's, I did not say that right, YouTube channel. Welcome, Sergiy.
Allison, thank you so much for having me, and welcome to everyone who's joining. I just want to reiterate the point about asking questions. Everybody, please do. I hate to give a monologue and would much rather have a discussion. But without further ado, let's get into AI and electronics. So we have had a little bit of an introduction. Allison did a wonderful job there. I don't think I need to repeat myself. But again, great to be here. Thank you so much. Let's start with the obvious, right? I think I'm guessing that almost everybody here has seen this screen before, right? ChatGPT became, one of the big, most recognizable implementations of AI that almost everybody has become familiar with now, and it's given people some of the first taste of what might be possible. With neural networks and large language models and whatnot. But like probably most of you, when I tried it out, and I was very impressed by its capabilities in terms of English and summarizing text. I was not very impressed with its capability to design electronics. That's not really what it was designed for. However, there's a lot of interesting work happening in that space, and so that's what I want to share about today. So roughly speaking, we'll go over some of the existing automation that has been done and is important in electronics as it is. The advent of neural networks, why they're important, what they can do for us, where they're going to be used. We'll cover some cutting edge research for the things happening in electronics by leveraging neural nets. And then I'll speculate and guess a little bit about what might happen over the course of the next 10 years and provide some practical advice and tools that everybody here can go to and start using to benefit their work today. So first, focusing on some of the success stories in automation. Automation in electronics design dates back a really long time. I was surprised by this when I first recognized this. The first paper I could find that attempted to, in this case, automate circuit board layouts, so both placement and routing of boards, dates back to 1962. So long before EDA, long before neural networks or anything of that nature, people were already writing papers on using graph embedding methodologies to try to design circuit cards, which is really interesting and interesting to see how far back it goes. So it's very much an old problem. Probably the greatest success story has to be in chip design. So as a perspective for how much automation in general, right, even without neural networks, has been able to do for us, this is a picture of the first microprocessor ever invented by Intel, the Intel 4004 in 1971. It had about 2,300 transistors, and it was designed by hand on a sheet of rubylith, the way that you see the person there literally etching it by hand, and then that was projected on the dies and manufactured. And for comparison, this is the cutting edge today, right? Today we have chips and wafer scale chips, from NVIDIA and Cerebras in this case, that are up to 4 trillion transistors, right? So we've gone up 9 orders of magnitude in terms of just the raw count of number of gates inside of a chip. And very clearly, that would be impossible without automation, right? I can't imagine scratching rubylith for 4 trillion different transistors. That certainly wouldn't be possible. Another big success that has, I think should be recognized is the synthesis of logic, right? So Verilog and VHDL synthesis for FPGA, also went through kind of a history. When Verilog and VHDL were first invented, they were actually used by the DoD to only simulate circuits, right? They needed a rigorous way to compare exactly what chips do, what inputs and outputs they have, what functionality they have. And then over time, people realized, hey, why simulate? Why only simulate if we can also generate? And today, you can get an FPGA and instantiate a Linux processor on it in a matter of a few minutes. Which is incredible. I don't know how many people here have developed for FPGAs, but that fast feedback loop is incredible to work with. Some other interesting things that maybe fewer people are aware of is that actual specific hardware design has also seen some amount of kind of automation and attempts to explore design spaces before neural networks existed. So before neural networks were a thing, common methods were things like genetic algorithms that would try to evolve shapes naturally to try to find some sort of performance. And so this is an example actually where this was applied for an antenna. This was an antenna designed for a NASA spacecraft that I believe eventually flew. And the antenna had some design parameters around, what angle it had to work well at, what kind of gain and bandwidth it would need to support. And NASA decided to design one kind of classically. That's what you see in the first picture on the right there. And then also to use a genetic algorithm to see if they can come up with a more, I guess, novel structure to do the same job. So in the top right of the screen, I have some examples of these kind of coat hanger wire looking things. Those are actual antennas that a genetic algorithm came up with the shape for. And what was interesting is already at this time, that antenna flew and outperformed the classically designed antenna by basically having, a far shorter design cycle, far simpler, didn't require like a matching network or a phasing circuit, had a higher gain in the specific bandwidth region. So already we were seeing attempts to use things like artificial intelligence, or what was considered artificial intelligence at the time, to design hardware. Another interesting example of this that I get a kick out of is an experiment where a professor tried to automate the configuration of an FPGA. So the idea was to feed in raw tones, from 1 kilohertz to 10 kilohertz, and have the FPGA create a discriminator that can distinguish between those two tones and tell you which one is going in. But the trick was that instead of writing a bunch of Verilog and VHDL to describe this kind of FPGA and what the logic should be, they simply hooked up a genetic algorithm to toggle all of the different configuration bits on and off until eventually the genetic algorithm came up with some of its own kind of unique, interesting configuration to do this task. No surprise that it worked. That's cool. This FPGA was able to distinguish these tones. But the interesting part is that by putting the hardware in the loop, this algorithm actually exploited the parasitics and the physics inside of the FPGA. So instead of only thinking about the FPGA design as what is the exact signal chain of all of these logic cells, it actually figured out how to use like coupling and things we consider to be imperfections in the FPGA to solve the task, which is really interesting and maybe a hint at some of the power that's possible when you put hardware in the optimization loop. So pivoting a little bit to neural networks and the importance that they have, I want to give some basic intuition. So for anybody who hasn't, designed a neural network before or worked with one, I want to dispel any notion that it's some sort of black magic or super complicated technology. They're actually in principle very, very simple. So a neural network is ultimately just a function, right? It takes in some information, it outputs some other information. To a large extent, a lot of neural networks, even to this day, are built with simple linear functions. So literally you can think, y equals mx plus b, where x is your input and y is your output. A good portion of any modern neural network, including the stuff inside ChatGPT, has pieces of it that work like this. And so some common nomenclature that people throw around to give some motivation to is that in a simple linear function, your m being your slope and b being your intercept, those in the language of neural networks are your weights and your biases. So when people talk about training a neural network, they're really talking about looking for m and b such that when you put in x, you get the expected y that you were looking for. So if you've ever fit a line to a bunch of data before in like a linear regression, you've done something very, very, very close to training a neural network. The trick with neural networks is that it's not just a single linear function. These functions are made nonlinear, even with something as simple as applying an absolute value, and then taken to an extreme scale where you have hundreds of billions of m and b weights, hundreds of billions of kind of vector inputs and processing and layers and so on and so forth. But the fundamentals are still the same. So as it's a function, these have been cast in a few different ways. So one of the first kind of interesting applications of neural networks, in my opinion, was the detection of handwritten numbers that get converted into digital numbers. So the first picture there I have is of Jan LeCun, a famous neural network researcher, in 1989, having a camera look at basically handwritten text and identifying the numbers in that text. And this is done with, again, a function that just takes an image, a bag of pixels, and converts it into an actual digital number. And again, it was trained in this way, similar to what I described with linear regression. Another big success that kind of really led to the first blooming of neural networks came in 2012 with the ImageNet competition. So pre 2012, when people were thinking about computer vision in general, not just for detecting numbers, but for detecting a car or a person or a motorcycle or a dog or a cat, this was all done with hand constructed algorithms. People were using heuristics and training basic regressions on top of them in all sorts of different ways. And this new neural network came around called AlexNet that was trained on directly all of the images and all of the expected outputs and outperformed all of the hand constructed algorithms. And so that was kind of the shot heard around the world for the initial kickoff of the efforts that have gone into neural networks, was that within the span of 1 year, all of computer vision research for processing images went from hand constructed algorithms and heuristics to training deep neural networks. But the interesting stuff, in my opinion, came even later on, right? So if we have these networks that can take in an image and output text, even at that time in 2012, people started asking, what if we can go in reverse? Like, could we take that network and make it run backwards so that when you put in text, you get an image? And of course, that started to show up some number of years later with things like Midjourney or OpenAI Dolly. And by now, we even have examples of being able to put in text and get a video, as OpenAI demonstrated with Sora. So some basic idea of how these networks are trained. There's a few different ways that you search for these weights, but in a basic sense, what most people are familiar with is this concept called supervised learning, where you basically take a bunch of examples to show the network and you make it memorize those examples, roughly speaking. So you take 10,000 pictures of an apple, 10,000 pictures of a grape, and for every one of those pictures, you tell the network, this is an apple and this is a grape. And that information gets distilled into the weights and biases such that in the future, when you show the network a similar looking apple, it will predict apple. And so that is the kind of classic method that people think of when training a neural network. Another interesting method, and actually probably more applicable to electronics, which is why I wanted to touch on it, is this concept of reinforcement learning. So in reinforcement learning, you never need to start with any kind of human labeled or human generated data. Reinforcement learning is designed, roughly speaking, to play games, right? So games like backgammon at first, and then chess and Go later on. The idea is to let the neural network just play the game over and over and over and over again, and learn for itself how to win that game. So roughly speaking, this process amounts to a random neural network starting to play the game, making random, silly moves that don't work very well, building a data set out of how that experience went, and then updating itself in such a way that the games where it tends to win, it tends to replicate those moves more frequently. And if you run this process, millions and millions of times, you end up with very spectacular performance. So most famously, I think, DeepMind was able to defeat the world champion at Go in about 2017 or 2018 by using this process. So with no human data at all, it was able to come up with strategies in Go that are better than any human. Um, so what's important about neural networks, right? Like, what is different about neural networks that didn't exist in the old optimization algorithms? Optimization algorithms existed for a long time, things like simulated annealing, genetic algorithms, min-cut methods, so on and so forth. But neural networks bring some interesting properties that we see research exploiting, and we'll go into. So one of those is memory, right? When you run a typical optimization algorithm, it solves that problem, and that's it. Like, if you have a new problem to solve, you can't reuse that work. You have to start from scratch. With a neural network, it can remember its experience and solve a similar problem very efficiently because of that. So memory comes up a lot. Another important property is interpolation. So within a neural network, one of the cool and interesting properties is that it doesn't have to see every instance of an apple in the world to look at a new apple it has never seen and still correctly guess that it's an apple. So by virtue of seeing so much data, it kind of finds a good representation of what represents an apple and is able to apply that to apples it hasn't seen. And we see that a lot as well. And the final one is differentiability. This is maybe a technical point, but the point is that it allows you to run the networks in reverse. So when you get an output, you're doing some sort of optimization problem and you got some sort of result, you can then see which way to nudge the inputs in order to make the output even better. And that's unusual. That's not something that optimization algorithms typically have. So let's look at some of the impact this is having in the latest research, and in particular, let's start with chip design. So the first paper that I'd like to present is Google's paper on designing tensor processing units with a reinforcement learning approach that was published in Nature, I believe, in 2021. The basic idea here is that when you're designing a chip, you have these big pieces of logic that you have to place called macros. So these kind of big purple squares, and then you have a whole bunch of standard cells or connections that are being made between those macros. And so what Google did is they handed over the ability to place the macros over to a neural network that then played this game of placement in a reinforcement learning algorithm approach. And then they used the standard EDA toolchain to place the rest of the standard cells, to wire everything up, and then ultimately evaluate power, performance, and area of the chip that they're able to achieve. And so what Google demonstrated in this paper was that the network was able to learn how to place the macros with an interesting strategy. In particular, it started to carve out a bunch of space in the middle for all the standard cells that are doing the interconnections and nudge all of the macros to the sides, basically. And this was able to achieve, a significant improvement in wire length of the chip. So specifically, they achieved a 3% improvement in total wire length. But the other impressive thing here is how much faster this is. So they estimate that for their chips, it would have taken about 3 weeks for someone to place all the macros, and the network is able to do that in a matter of a few hours. Another example of this comes from NVIDIA. So they are also looking at, how to improve chip design, and they took an interesting, different approach. So instead of placing macros, what they decided to do was to have a neural network predict clusters that the standard EDA tools should consider more heavily. So the idea is that with the standard EDA process, you can tell the tool to put certain components or certain cells next to each other. And as a designer, you use that lever to try to make a more optimal design. And in this case, NVIDIA used the graph neural network to choose those clusters automatically. And still reuse the same EDA tool flow that exists to do the actual placement, the actual routing, the actual parasitic simulations, and all that stuff. And again, they were able to achieve stronger results than with human and classic efforts, right? So they were able to push that chip 20% higher in frequency, and again reduce wire length and clock power with an approach like this. Another interesting thing that I saw was this paper focused on parasitics. So this is a pattern that we'll also see in some of the later papers where neural networks can kind of speed up some of the slow running processes of doing simulations that are impacting design. And because they can do that, they can also speed up the entire flow of designing whatever it is you're designing. So in this case, this paper demonstrated trying to predict the parasitics of a circuit based only on the circuit schematic. So in this case, they're looking at like an op-amp schematic, at a transistor level. And, the statement is that typically at this point during the schematic generation, a human might take a guess at what some of the parasitics might be when this is actually converted into a real layout, right, into a real chip design. And humans are, obviously not perfect at this. And so they have some imprecision and error, and they have to wait until the layout is done and a simulation is run to actually determine what the parasitics were and how to kind of account for them. What this paper showed was that a neural network could be trained, a graph network in this case, that could take in the schematic and make that prediction about the parasitics only from the schematic. So before you even attempt layout. And these estimations were within about 10% of the actual true simulated values. And so that's something interesting where before you even start the layout, you can give the designer some relatively high quality feedback on what to expect when the layout will actually be done and the parasitics are extracted. Switching a little bit to logic synthesis, there's some interesting work happening in basically how to even assemble logical cells. So in this case, this paper was looking at the design of these things called prefix circuits. So for basic intuition, for somebody who hasn't seen this, if you want to add two numbers, right, two 64-bit numbers, for example, there's many different ways to kind of aggregate all of those different inputs and find the resulting number. And for the sake of a fast performing chip, you want to perform as many of those operations in parallel with as little delay as possible. And so people study these different architectures or these different kind of flow diagrams or these graphs of how to put together prefix sums in order to achieve, a very fast and very parallel, adder or incrementer or any other kind of circuit. And so in this case, the neural network was given the access to control what this tree structure should look like. So how exactly do we combine the prefix elements to achieve a 64-bit adder? But then it was also trained as a reinforcement learner with the full EDA toolchain in the loop. So it would propose a tree structure for how to combine the prefixes. It would actually synthesize using standard EDA tools, synthesize the circuit, estimate the final kind of delay of the circuit and the area that it takes, and it was able to achieve a 30% lower area for the same delay of a 64-bit adder, which is better than the commercial tools even have in their standard libraries. So all of that I've discussed in the past, I should have said earlier, does not rely on large language models, just to make it really clear. Like large language models are functions that take text and spit out text. That doesn't help you when you're doing physics or parasitics or graphs or things of that nature. Different structures make sense there. But text makes sense when you look at just generating, Varicode or Verilog. So what this paper was studying was how good are LLMs, even like ChatGPT, at solving problems in logic synthesis and in Verilog and VHDL in particular. So they took a data set of over 100 different problems. These are probably toy problems, simple one pagers that you might ask in an interview. I'm sure it's not an entire chip design. And they would pose those to the neural network, LLM, and ask it to actually generate the Verilog code that could solve that problem. By running that alongside a classic Verilog simulator and validating whether or not the solutions are working and doing a little bit of feedback loop with LLMs, they were actually able to show that almost 60% of those problems were solved correctly entirely by the LLM. So there's some evidence, probably just because there's a lot of Verilog code out there on GitHub or on Stack Overflow, that GPT-4 and ChatGPT are actually decent at proposing some Verilog or VHDL as at least starter code for your projects. Switching over to simulations, there's a lot of research happening right now between NVIDIA and ANSYS and different laboratories about speeding up simulations with neural networks. So in this particular case, we're looking at a scattering problem where we have a perfect electrical conductor, like a circle in the middle in a 2D grid, and we're launching a plane wave at it. And we're trying to measure the scattering that's going to happen with respect to that perfect electrical conductor. And typically you'd run something like a finite difference time domain solver for this, and it might take 10, 20, 30, 40, 50 minutes, depending on your resolution and parameters. And so the intent here is, can we make a neural network that basically comes to the same conclusion, that takes this kind of scene information and the initial electric field as an input, and then puts out the final output of the simulation. And in this case, this paper showed that that's not only achievable, but the neural network ends up running 20 to almost 600 times faster than the classic simulator, which opens up a lot of possibilities. So another example of that is in the field of optics. So people are in the field of photonics, people are designing these nanostructures to process electromagnetic waves. And in a similar way, you'd have to run these big simulations, and instead you can use a neural net to do the same thing much faster. But in this case, this paper showed that you can kind of put that into a loop and design these device structures with just as much accuracy and precision as a human does, with the same final efficiency, but much, much, much faster, about 7,000 times faster than running a classic simulation. Finally, a couple examples in antenna and filter design. So this is an example where a filter is being designed for a chip in the terahertz range. The idea here is that the filter is a distributed filter. So instead of using like fixed lumped inductors, capacitors, resistors, it's just using raw copper that can be etched onto the substrate to then do bandpass filtering, basically. And so in this case, the neural network was trained to to see a shape of a filter, see the actual physical copper arrangement, and to predict what its basically S parameters would be. S parameters are a measure of what kinds of frequencies are passing, what kind of frequencies are not passing. And then again, as in the previous paper, used in reverse, the neural network can propose an architecture for such a filter that matches some design specs. And so in this case, a human took 3 weeks to design a filter that produced the response curves on the right, and a trained neural network was able to do the same thing in just a couple of minutes because it can predict the performance that's so much faster. Similar story with antenna design. Same kind of concept where you can teach a neural network to see the shape of an antenna and predict its gain pattern. And with that, you can basically run it in reverse and design an antenna from scratch that gives you some sort of performance in terms of what the bandwidth is, what the central frequency is, and what the gain you want to achieve. And then finally, in PCB design, we're seeing some amount of reinforcement learning applied to autorouters, where instead of just running kind of basic maze solvers that find a path from A to B, we can train to have networks recognize signal integrity problems and crosstalk problems. So in this case, this paper demonstrates the ability for an AI-based router to find a path that is also short, but that avoids other nearby signals to try to eliminate the crosstalk. And for evaluating placement, another paper demonstrates the ability to predict whether or not a given placement of a board is actually routable. So at this point, the idea of the paper is that if you arrange the components in a certain way, it might actually be impossible or very, very difficult to route that board. Some classic heuristics exist in EDA software to accommodate this, but neural networks can do a better job predicting this kind of heuristic and to tell you if the board will be routable. And final interesting kind of case here is actually in thermal design. So NVIDIA has a set of pre-trained neural networks that estimate computational fluid dynamics. And with that, you can predict the airflow through a heatsink and measure how much power it's going to dissipate from the chip that it's cooling. And so NVIDIA was able to show the design of a heatsink, in particular to how the fins on it should be arranged, that happens within hours by using one of these fast physics predictions, as opposed to weeks for a kind of more classic process. So, as a concept for where I think we'll be in the next 10 years, I think the theme is that hardware is going to look a lot more like software design. So software design has a bunch of different benefits. For one, we have compilers, and we can kind of focus on high-level logical abstractions like code and get ones and zeros as an output almost instantly and see the efforts of our code happen immediately. And so I think something similar will happen with board design and to some extent chip design that hasn't happened, where we'll be able to work on our schematics and immediately see the kind of board that produces. And if you have to jump to a more difficult stack up or a bigger board size than you intended, and so on and so forth. Another example that shines in software engineering is the process of continuous integration, continuous development. So when a software engineer writes a piece of code, by the time it finishes all of the tests that run automatically, they can be very confident they did it right. In hardware, of course, that's much, much harder and much slower, if existing at all. So I think that we will see tool chains like this where when we make changes to schematics and we make changes to layouts, we can be very confident that the board will still work rather than manufacturing and kind of hoping for the best. Another interesting thing that has happened in software is the abstraction between the code that you want to run and the servers that run it. So with containerization, you can just as easily write code to run on AWS or on Google Cloud and so on and so forth. And so I think that similar tools will come up that allow you to more easily consider multiple manufacturers and to determine, how you can use the benefits of a specific manufacturer to achieve boards that maybe others can't. And finally, ultimately, I think all of this will result in lowering the barrier to entry, right? So nowadays, a 10-year-old can write code. A product manager can do some basic design in Figma. A complete novice can make a website. And it's led to just a lot more people having access to software and the benefits of software. I think that the same thing will happen in electronics design over time. So some examples of things you can use today, we have there's a whole bunch of products that are already available. They're starting to scratch the surface at this. So within the chip design space, Cadence and Synopsys have a good set of tools to start to exploit some of the papers that we've already seen. In the PCB design space, companies like CircuitMind, ourselves at Quilter and Flux, are providing tools to automate schematic generation. In our case, automate PCB layouts. In the case of Flux, to have a co-pilot experience that helps you kind of chat with your schematic and understand what's going on and that kind of thing. And Mitai is focusing on identifying issues in your layout of your PCB. And finally, ANSYS has a lot of quick accelerations that are used with neural networks to make full end-to-end simulations much faster. And finally, last shout out for us, Quilter is in open beta. We focus on the PCB layout aspect in particular. Anybody's welcome to come, sign up, and try the tool out. And please give us feedback. And that's it for the talk. I'll take any questions.
Okay, so I have a couple of questions. One is, where does the training data come for the AI that designs the PCBs?
Yeah, that's a great question. So, if you recall back to the discussion about how different neural networks can be trained, right? There's supervised learning and reinforcement learning. So a lot of people tend to assume that the right way to design a PCB would be to start with supervised learning, where you take millions of human board designs and you train a network to do the same thing. What we're seeing in research and what we're doing at Quilter is actually not like that at all. What we're doing instead, and what a lot of the papers do as well outside of our company, is to phase PCB design as a game where you can, place components and route things and so on and so forth, and then evaluate them against physics, right? Evaluate them against basic DRC rules at the minimum, but then ideally, eventually, thermodynamics and electromagnetics. And so with that, you don't need any data at all, right? The neural network can simply try a certain PCB layout, and then assuming that it has the information required to know that we have differential pairs and high-speed buses and high current set traces and so on and so forth, it'll figure out how to arrange those such that all of the physics and parasitics and manufacturing checks out. So that's what I expect will happen in most of these design cases. I don't think there's enough data out there to make supervised learning work well. I expect to see reinforcement learning as the dominant method.
Yeah, I have a personal non-engineer question. So, Chat GPT, we've learned has been trained by everything from Wikipedia articles to everything online. But because PCB designs are, very private, protected data, how will you develop a robust, neural network if without access to, or as you're saying, I think you kind of answered that question, but maybe if you could kind of elaborate a little bit on that.
Yeah, absolutely. So of course that is very much the status quo that like companies do, and as well they should protect their IP, and it's not just on GitHub and Stack Overflow. And furthermore, I'll even go so far as to challenge that humans are only so good at designing circuit boards, right? Like if you had imagine 100 years from now a super crazy level of artificial intelligence, it's not inconceivable that it'll come up with strategies and methods to make boards smaller, cheaper, faster, with fewer layers, by taking more into account than humans really can given the time that we're given. So I think that really the point here is to focus on grading the circuit boards against what really matters, right? You start with some schematic input. One of the common things that people do when training reinforcement learning is they create what's called synthetic data. So where you basically say, hey, let's just generate a proposed schematic, right? Like it doesn't have to be exactly real, but let's throw in a processor and let's throw in a memory and let's define that it's DDR3 and so on and so on and so forth. And you can create millions of such cases. And then you give those cases to the network to say, hey, go solve this, right? Like go actually find a PCB layout that puts everything on the board, meets all the manufacturer specs, minimizes layer count, maximizes things like, basic trace width and whatever. But then more importantly, like checks all of the crosstalk, checks the signal integrity, checks the I diagrams, and the S parameters of everything. And only if everything on that physics list checks out, do you get a win in that game. And it's going to take a lot of computing power, of course, but by giving the neural network the ability and the access to playing that game over and over and over, and then seeing if it actually succeeded against classic physics simulations, that's how it'll eventually train. And it'll be able to, because of interpolation, it'll be able to transfer that experience to an actual board by a customer.
Mhm. Okay, so one of the questions is, do all constraints need to be defined by a human, or can the AI estimate those as well?
Oh, that's a great question. I think that in the future, it's going to be less and less necessary for humans to define it. So In PCB design in particular, most of the constraints that are present on the board can be derived from the data sheets, right? So if a human inherits a schematic that they didn't design, they can pull up the data sheet for every single chip and study it and study the schematic itself and get some pretty good idea of what the board was meant to do and what the operating parameters are. This is actually a great application for LLMs. I think that LLMs are showing the ability to read text, unstructured text, and even unstructured images quite well. And so I think they'll be able to scrape a lot of information out of data sheets and make some of these conclusions about this is likely a 4 amp trace, this is likely a 3 gigahertz signal, so on and so forth. So the roadmap that I roughly see is we'll start with at first purely human entry, which sucks. Then LLMs will start to pre-populate a lot of that information, and the human simply reviews it and supplements or corrects anything the LLM didn't get right. Eventually, LLMs will be, I don't know, 99% good. We'll still have to ask questions about like what's on the other side of this connector, or what if it's a custom chip that you're Apple and you created and the data sheet doesn't exist. And eventually, what I really think will happen is EDA tools will incorporate that core information about what's happening in terms of signal at every pin into the actual consideration when you create a schematic. I think that eventually we'll start to see schematics more like code, and code has complete information about the design intent. And I think we'll see schematics eventually have the same kind of parity that code does.
Okay. So there's a question regarding patents, and it says patents for CNN, FFNN, and RNN for routing, placement, and specifically to the concepts of topological routing, signal analysis, antenna design is very long, but it goes into a lot of things that are patents that are held by ANSYS, Cadence, Synopsys, Siemens, IBM, Intel. So it's basically asking how will you license those, because these companies are known to protect their patents. So that's kind of it's a longer question, but I think you can answer
Sure.
that.
Yeah, gladly. I think nothing about AI or neural networks changes this from prior art. The patents existed for classic optimization algorithms and technologies and so on and so forth, and they will continue to today. Any startup has to, or frankly, even any incumbent has to, come up with their own algorithms, look at the existing patents, prior art, see where they're too close or where they can go further away, and how to not infringe or license when they have to. But the thing is that I actually expect that it won't be so difficult, because patents, by definition, have to be rather specific. They have to be very concrete about how some idea is implemented. Of course, companies try to make it as general as they can, but the job of the patent office is to make it specific. And the cool thing about what's happening in AI right now is that there's new algorithms and approaches being born every day. And so I think that for the same kind of problem, we're going to have more and more and more types of solutions. And I don't think it's going to be hard to either license or just find a slightly different approach to still get the job done.
Okay, there's a question about EMI. Sometimes for layout of PCBs, positioning of components affect EMI or other side effects. For Quilter, for instance, for designing switch mode regulator layouts, does the software consider the EMI effects while positioning of the components such as capacitor, inductor, or resistors?
Yeah, great question. So very plainly today, no. Today, if you come to Quilter, when you go to our constraints definition, you will see everything that we consider. And the fact that something is a switching converter and has a certain switching frequency and certain powers is not there. And so Quilter will not consider it, and it won't be accounted for. That's an example of the kind of thing that we'll be adding in and building out over time. I certainly think it's possible. I certainly think we have all the pieces there to eventually do it. Not an easy problem, but eventually we'll solve it.
What is the most complex design that this model is able to design in terms of number of nets and number of PCB layers?
Yeah, sure. So in general, the kinds of boards that we design today are on the simpler side. So the goal is typically to keep the layer count fairly low. Most of our designs are 4 layers, 6 at the most. In terms of number of nets, the most complicated design we've ever done is about 2,000 pins. That's probably about 13 to 1,500 nets, something of that nature. I think that design was about 300 or 400 components. And but that design didn't have a lot of power or high frequency components or anything like that. Basically, just a big big test board, big breakout board, and it did fine. We were able to manufacture it and work just fine. In terms of kind of signal integrity, the most interesting design we were able to handle was computer vision design. It's actually available on our site if anybody wants to see it. It's a recreation of the OpenMV board, which had an STM32 running at 500 megahertz, connected to a camera, SD card, USB 2.0, and all of that able to run computer vision algorithms on board, power a screen, and do basically live computer vision. So those are roughly speaking the kinds of boards we're designing. If you're thinking about uploading a computer motherboard, we're not there yet.
Okay. And so someone is asking, which I'm not sure if you'd have time today, but I'm sure you set up another webinar, but they would like a live demo on how to use Quilter and what are the inputs to generate the AI routed PCB.
Yeah,
So
I will take that as an opportunity to request another webinar. That sounds like a lot of fun. Yeah, in 2 minutes, I think we won't cover it well in enough time, but I'll give the basic parameters. What we start with is, we ask you to upload your schematic and the beginnings of a board file. So your typical process of designing schematics stay the same. Your process of, importing that into a board designer stays the same. You draw the board outline, you place the connectors. And typically people will upload just that to us. So you place the connectors, the board outline, provide us with a schematic, and then we'll do the placement, routing, stockups, pours, and everything else at that point. That's the rough flow, but yeah, full demo, I think we should reserve another time.
okay, and then one more question. Many LLMs are prone to hallucination, which could cause big problems in the world of electronics engineering. How do we avoid this?
Yeah, that's a really critical question. So I think that we're really very, very far away from the concept of operation of how ChatGPT works, right? With ChatGPT, you type in some text and it directly predicts the output text that you see, similar with Midjourney or Stable Diffusion or so on and so forth. And of course, they are not required to have precise outputs, and therefore it's acceptable to have some imperfections. I don't think we're going to see something equivalent to that in circuit boards or chips for a very long time. Instead, what I see is neural networks doing planning on top of more classic software that restricts the board design to allowable parameters. So instead of just saying, hey, neural network, it's up to you where to put two components, and it might make them collide and it might make them not be placeable, instead say, hey, pick where you want to place them. It proposes placing them a little bit too close, and then a classic piece of code says, oh, you can't do that. So the closest you could do is here, where there's still some tolerance. So if you let the neural networks have long-term plans and long kind of high-level design capability, as many of the papers showed, and then do the details with classic, good, rigorous code, that's how we can balance the two in the near term.
Okay, there's one last question. Well, actually, one just popped up, which says, "Can you do blind and buried vias?" Which I know that I'm guessing not yet, but but go ahead and answer that.
Yeah. Yeah, not today. It makes our life easier because it's easier to route when you don't have to span all 4 layers. But practically speaking, the kinds of boards we're handling today just don't merit it. It would be a waste of money to use something like that for the kind of density that we can handle.
Okay. And then similar to the recent question, suppose the AI created design is copyrighted by the creating company. What happens when another company creates the same design?
Well, you could only create the same exact design if you had exactly the same inputs. So like it would be impossible unless the second company had exactly the same schematic with exactly the same inputs and outputs with exactly the same parameters. And even then, like within Quilter, you have so many choices about, do you want to do this with 2, 4, 6, or 8 layers? Do you want to have certain clearances? Eventually, will allow you to control floor plans and other kind of opinions like that. I find like if that really happened, I would say that probably the second company already somehow got the inputs of the first company, and the infringement already happened at that point.
Okay, so one question was just what CAD softwares can you use for the schematic input into Quilter?
Yeah, so today we support Altium and KiCad.
Okay. All right, so I don't see any other questions. I do want to let everybody know that we are going to be emailing the recording as well as the slides for this presentation. And if you have any other questions, I encourage you to reach out to Sergiy to find him on LinkedIn. And then if you have any questions regarding manufacturing, you can reach out to me, allison.herrera@summitinterconnect.com, and I'll put you into contact with your sales rep. And really thank everybody for joining us today. And Sergiy, thank you so much for this presentation. It was really, really awesome.
Awesome. Thank you, Allison, and thank you everyone for attending and the great questions.
Okay, bye everybody.